I want to talk very specifically about the differences between reinforcement learning and traditional AI learning, and training, which would be supervised learning and unsupervised learning. And so, in my experience and in my mind, most people start off and they go through a progression, which is supervised learning, unsupervised learning, and then maybe they do or they don't dive into reinforcement learning from there, depending on what their interests are. And like 90% of people don't dive into reinforcement learning from there because it is 100% different than supervised and unsupervised learning. And supervised and unsupervised learning are hard enough to learn in and of themselves, but then going from there and then learning this new concept on top of that can be kind of strenuous and hard for a lot of people, and I understand that. So with this video, I want to kind of dive deeper into these things and give you a clear understanding of the differences between reinforcement learning and supervised and unsupervised learning, and kind of give you a crash course, things to look out for, and then just general introduction to these things. If you're looking to get into reinforcement learning, you have some sort of exposure to the back end of understanding how to train models. You've dove deeper into NLP models, LLM models, etc., and you want to take that next step. This is the video for you. So diving into it specifically, off the top, a lot of these programs, so there's a few different frameworks and environments that you can operate within. There's OpenAI Gym and Ale are the two primary ones, and I'm running Ale in this instance, and then it's just whichever one is generally your preference for libraries. And then in this instance, I like Ale because it comes with all these ROMs preloaded, and I can just load the ROMs in the games, and then it's like 50 Atari games, and then so it's like Breakout, Pong, Q*bert, Pac-Man, games like that, Pitfall, Frogger's not one of them, and then so there's different games that you can play and go through and train the models in this instance. And then so what do you train these models on? Well, you train these models on environments, right? And then so in this instance, we're looking at Breakout. So this model is being trained on Breakout in this environment. And then so in this instance that we're looking at, how it gets trained on is the first major difference is that with reinforcement learning, you deal with reward functions as opposed to inputs and outputs. And then so with the reward function, what this means is primarily and upfront, you don't have back propagation within reinforcement learning. No back propagation whatsoever. Big concept there, right? And then so the reason why you don't have back propagation is because of the fact that it wouldn't actually do anything in this instance, right? So back propagation, what it is you're feeding the errors back through the model. But in this instance, what you're doing is this model is exploring the environment. The errors aren't known, right? And then so we do not have a known error in this instance. So there is no back propagation in this instance. But with that being said, if you're familiar and you've seen kind of videos, or maybe you've seen things around Q-star, Q-learning, when it comes to reinforcement learning, the Q-learning algorithm is kind of a, let's call it a way to do back propagation without actually back propagating the data, right? And then so it's Q learning is essentially just keeping a log of the environment and of this, like of the memory, right? So it can go back and it can see what it, like a Pokédex is how I like to refer to it in my head. But so within that instance, it's does kind of a lot of what back propagation does, but we're not doing back propagation in this instance. So you have, first thing within that is that you don't have gradients, and then so you don't have to deal with like a lot of the complexity that you have to deal with the back propagation. Back propagation introduces a lot of mathematical and then therefore computational complexity that is not present within this. So that's good in of that self there. And secondarily, you can create different shapes on the back end of these models. And then so you'll notice like when the Google DeepMind team, when they train models like on video games or whatever they train them on, etc., right? They're these are different models than say Gemini, right? And then it's because they're completely different architectures. Again, there's no back propagation is the big thing, but then secondarily, I can do and I do things within this architecture that I wouldn't do within other architectures, because I'm not in this instance trying to predict next tokens. I'm not trying to predict really anything in this instance. I'm trying to predict and learn about my environment and then base my predictions based off of the learning of the environment. And then so in this instance, I'm looking more for exploration and then control of that exploration. And then so if you see in this kind of background that's been running here, you'll see that it's in here, it's been initializing, maintain, decreased. And then so that decreased is with regards towards the exploration within this mechanism, right? And then so within the exploration, what I can control is essentially the rewards that the model is being given within this instance. And then so the rewards that the model is being given in this instance dictate exactly how its behavior is going to function. And then so in this instance, I have it essentially set to explore. Number one rule is that it's to explore. If it starts finding patterns where it's hitting the ball a lot and getting a high score, then it's to decrease its exploring and decrease its exploration and then focus more on hitting that ball. And then that's what we're seeing here, right? And then so the goal is kind of to guide this model more and more towards hitting this ball more and more, right? It's just very simple and very straightforward. And then so the model in this instance has been doing a decently good job of hitting this ball multiple times. So we can see that its exploration was decreased a little bit in its last training run. We're saying, hey, you're doing good, right? Keep up what you're doing. Let's decrease the exploration a little bit and then just keep doing exactly what you're doing. And then that brings us into kind of the secondary concept and the most important concept that I'll spend a lot of time highlighting, and I'll showcase it in multiple ways within this video, is that with reinforcement learning, the individual environment and every single detail about the environment matters more than anything else, right? So in this particular instance, we're playing a game called Breakout. And then so Breakout is interesting, right? And this model that we're looking at has been training for about 20 minutes. And this model is doing decently well, especially for only being 20 minutes old. Right? This model was essentially born 20 minutes ago, and this is its performance in Breakout, which is, I mean, decently old for a little baby. Yeah, decently good for a little baby. And then so within this particular training of this particular game, I've set up these parameters of this model very specifically for this game. So very specifically within Breakout, it rewards you every single time that the ball hits the paddle and hits the bricks, right? And very simple. And then so within that, you can put positive and negative rewards within your reward function as an example highlighting this concept. If you just put positive rewards for Breakout, for example, your model is not going to learn efficiently. So you see in this instance here, we can see that the training times, it's estimating that it's going to take about 5 to 7 hours to train this model fully. If I just had a positive reward function on here, this would jump. It would be like in the 20 hours, 20, 30 hours, just flat out, just to learn Breakout. I've made this algorithm that we're looking at here very efficient for Breakout in and of itself, right? And then so with the positive reinforcement algorithm, it will reinforce it every single time that it gets a positive score or it hits bricks. But within Breakout specifically, there's multipliers, right? Like if it hits those yellow bricks, it gets a massive score multiplier. So if you just put positive reinforcement in, what will happen is within a few hours of learning, this model will learn that if it gets and it hits those yellow bricks, it's going to get a better positive reinforcement score than doing anything else. And then so what it will do is it will take its 5 lives and then it will just maximize it to hit those yellow bricks and then get a score of 11, which if you're looking at here is a score of 11 is higher than this model is like getting right now based off, and that's based off of lots of hits, right? Because of that multiplier, like that yellow multiplier adds a lot. And then that matters to the model as far as that reward, right? Like that yellow reward is 3 times as much as the green or the blue. And then so the model will in essence just train and maximize towards that. So if I just put positive reward in this and no negative reward when it comes to this particular game, within 2 hours this model will be broken because it's just going to maximize that towards hitting that yellow. And then the other thing it's going to do is it's not going to learn as much about hitting the ball with the paddle. So within this I have 2 things. I have 2 rewards in this code that we're looking at here. Code number 1 is reward every time that it hits the bricks, and then code number 2 is negative reward every single time that the ball misses the paddle, and then so the paddle misses the ball. And if you don't put that negative reward, it just doesn't care. Like it won't move the paddle half the time. It won't go to chase that ball. And then we can see, we can actually look at a good example of this. I'll run Gemini Pong. This is an example of Pong versus breakout game. And then what we see here is that this model in this particular instance is a lot less interested in hitting this ball, right? This is an example and a showcase for you of positive rewards only versus implementing negative rewards and positive rewards. So in this instance and in this model, this particular model has a lot more computation, training, brains, etc. behind it, like a whole lot more than our breakout algorithm that we're just looking at. What we see here just for the very first time is when it hits that ball, right? And my expectation is this is not going to do it again before this resets at 20. And then so within that, like what we can see is that it's, and the major differences between this one and the one that we're looking at, no negative reward function in this, only positive reward, right? So it's only getting rewarded every single time it scores. It's not getting a negative reward every single time that ball misses the paddle. And so you can see in a lot of instances, it just doesn't care. It's letting the ball fly by. And then as we train this model more and more, a couple of hours in, it's just going to let that ball fly through. It just doesn't care, right? There's nothing in it to tell it to care about actually hitting the ball, which is a problem within this, right? It's that's a part of reinforcement learning, is within the environment what exactly it should and it shouldn't care about, right? It's like it's kind of counterintuitive within this. To me, the best way to look at this and to think about it is to let's look at it like at a game like Cubert, right? Looking at how AI plays Cubert is a lot better. Oh man, this is kind of messed up, but we'll be able to see it still, I think. But so we can see like Cubert is a lot different of a game, right? And than these other two that we're looking at. It's just pure exploration, but you can see that the model does learn in this instance. It will get better and better as it goes through, but I'm going to close this because it's just kind of, there we go, kind of annoying at that instance. And at that point, seeing all of that just fly by. But so like this is more of a, like you can see as a human a lot more what's going on within this game and what the model is thinking and its approach to things within this, right? But kind of the bottom line is that like this model is just exploring off of pure random exploration. It's not thinking or utilizing any sort of human learning type concepts. But if you think that the model's not learning, just let this run for an hour, half an hour, you'll see, right? Like, so right now it won't get past level 1. If we let it run for 45 minutes, it's going to get past level 1. And so it's very clear and easy ways to see that the models are actually learning within this instance, right? And then so within that, what you can control, and kind of the bottom line and the last thing to touch on within this video is, so how exactly and where exactly are you controlling these things within this? So let's take a look at the code on these things on the back end. So with our breakout, it's more simplistic, right? So the very first thing is again, I mentioned Q learning. So everything comes back to like Q learning. So I'm running DQN algorithms in this instance, which is like taking that Q learning algorithm and that Q learning concept and then shaping it into a neural network, a feed forward only neural network. And then so that's what we do here. And then so you'll notice that a lot of this code, all of this code is all mathematics, right? And then so what you're doing is you're really like literally creating mathematical shapes, creating tensors, and then you're creating exactly how you want those mathematical shapes and those mathematical objects to interact with each other. That's literally all this is, right? All of these are individual mathematical equations. Defining the training step, this is more mathematical equation. Here's the agent. Here's all the math for the agent, right? And then so you can see, like, it is all math, and there's no way around that. And then so how do I, like, I'll flat out, how do I code out like math for breakout that is completely different than math for Pong, which is completely different, 100% different than math for Qbert, right? Like, and we can see that the shape of our dueling DQN is totally different here, depending on the game that we're running here, right? So classic dueling DQN, we can see that the convolutional neural network, just from looking at this, right, the very first ones, we can see that the shape is totally different for these, right? Like this shape is like just the code is different, right? So it's different math overall is kind of what I'm trying to highlight. And then what I'm trying to highlight within that is that I don't sit here and then just hand write out all of these mathematical equations. I have kind of at my exposure and fingertips, how I look at it is I utilize Wolfram GPT as my favorite model. Wolfram GPT scores and calculates the master's level with regards to course math theory, and then so that's cool enough for me, right? I can consult someone that has a master's degree in math, and then they can help me shape my convolutional neural network. And then sometimes I do get the math wrong, right? Like we're looking at the Qbert. What we're looking at here with this code is it's still running. It might have bricked, not still running, but this is a math error, right? And then so this is all like, we can see shape after a convolutional shape after shape input. You can see it's going through, but I need to fix math within this. And then that's what's messing up within this. So the bottom line is that this is all fun. It's all easy to do. It all comes down to the environments and how you shape the environment, the ways that you can control it. You have so much control and different things that you can do to play around within the environment. It all comes down to math, understanding math, and playing around with math. And then there's no avoiding that, but you can rely on and utilize AI to help you within that instance, to help you build out the math. And then so just highlighting overall and then recapping two big differences between, in my mind, for reinforcement learning as opposed to supervised and unsupervised learning is feed forward only, and then the reward function exists. And then the last thing I'll highlight with reward function is important to highlight in my mind. The reward function doesn't replace the attention mechanism. You can have an attention mechanism and a reward function. And in this instance, my DQNs don't have an attention mechanism in this instance, because I think, like in my experience from this, the attention mechanism is not beneficial in a lot of instances for reinforcement learning. It can be, and there's instances where you can make it beneficial, but like overall, attention isn't all you need all the time. Is kind of how I look at it. But there's theoretically nothing whatsoever stopping you from having an attention mechanism plus a reward mechanism. They're two different concepts. And then so with that overall explained, I hope you like this type of content. And if you do, please like and subscribe. Thank you very much.